Hey Thinksters, and welcome to my new FooBar challenge. So this is I think the third level of the Google FooBar challenge. I got invited to participate in the challenge, and yeah, so I want to share with you how I solve these problems shared with Google. So many Thinksters requested some live coding sessions, so I thought it might maybe a fun thing to share them. Okay, so let's dive into the FooBar challenge. So here, if you got invited by Google FooBar, you get this account. It's like the environment is like a scripting environment. You have already seen probably the other videos, and yeah, so you there are different commands you can type in help to see the different commands that are available. And now let's see the status. Okay, we see, so I'm currently at level 3 and I've completed 33% of level 3. And so I also got this link, this share with your friend FooBar invitation link, and I shared it with the Thinkster community. So there's one more Thinkster user invited to the Google FooBar challenge, but it's already used. So it's unfortunately it's only one link I can share with an interesting Thinkster. So this is already done. But let's dive into the level. Okay, so so first look at what's in a journal. Success, you've managed to infiltrate Commander Lambda's evil organization, and so on. So this parts of it we have already read. Okay, parts of it is completely new, like here. The latest gossip in the henchman break room is that Lamp Job stands for Lambda's antimatter biofuel collision hadron oxidating potentiator. You're pretty sure it runs on diesel, not biofuel. Okay, this we already have. You got the guards to teach you a card game today. It's called Fizz Bin. It's kind of pointless, but they seem to like it, and it helps you pass the time while you work your way up to Commander Lambda's inner circle. Awesome. Commander Lambda was so impressed by your efforts that she's made you her personal assistant. You'll be helping her directly with her work, which means you'll have access to all of her files, including the ones on the Lamp Job Doomsday device. This is a chance you've been waiting for. Can you use your new access to finally topple Commander Lambda's evil empire? Who the heck puts clover and coffee creamer in their tea? Commander Lambda, apparently. When you signed up to infiltrate her organization, you didn't think you'd get such an up-close and personal look at her more unusual tastes. Okay, so first of all, I'm going to copy this. Let's make it a new file. Okay. Second of all, let's read the start here document. Type a request to request a challenge. Okay, so let's request a challenge. And we are in the next challenge. So we have time for this. For full injection perfection is 3 days, 23 hours, 59 minutes, 49 seconds, and it's added to the home folder. Okay, so let's copy this as well. Should we check out? So here you see it's a new folder, full injection perfection CD into this folder, and let's see. Again, we have like a Java file, a solution.py file, README, and some constraints. So let's start with the README. As a coder, you always start with the README, and yeah, so full injection perfection. Commander Lambda has asked for your help to refine the automatic quantum antimatter full injection system for a Lamp Job Doomsday device. It's a great chance for you to get a closer look at the Lamp Job and maybe sneak in a bit of sabotage while you're at it. So you took the job gladly. Quantum and antimatter full comes in small pellets, which is convenient since the many moving parts of the Lamp Job each need to be fed full on one pellet at a time. However, minions dump pellets in bulk into the full intake. You need to figure out the most efficient way to sort and shift the pellets down to a single pellet at a time. Okay, the full control mechanism have 3 operations. Add 1 full pallet, remove 1 full pallet, divide the entire group of full pallets by 2. Due to the destructive energy released when a quantum antimatter pallet is cut in half, the safety controls will only allow this to happen if there is an even number of pallets. Write a function called solution n, which takes a positive integer as a string, okay, and returns, so we need to convert it, and returns the minimum number of operations needed to transform the number of pallets to 1. The full intake control panel can only display a number up to 309 digits long, so it's a huge number. So there won't ever be more pallets than you can express in that many digits. For example, solution 4 returns 2, because we can have like 4, 2, 1. Solution 15 returns 5. 15 to 16, increase 1, then divide by 2, divide by 2, divide by 2, divide by 2. Okay, so test cases, your code should pass the following test cases. Again, we have solutions 15 and 4. And we submit the code then later. Okay, so let's quickly copy paste this. For the course. And again, have a read at this. So you need to really understand the problem before you can start solving it. Okay. So I'm open the drawing board here. Start drawing. Okay. So again, quantum antimatter full comes in small pallets, which is convenient since the many moving parts of the landscape each needs to be fed full 1 pallet at a time. 1 pallet at a time, okay? So we add 1 pallet, 1 pallet, 1 pallet. However, minions dump pallets in bulk into the fuel intake. So we add 1 pallet and one pallet and then they dump it. You need to figure out the most efficient way to sort and shift the pallets down to a single pallet at a time. To sort and shift the pallets down to a single pallet at a time. The full control mechanism has 3 operations. Add 1 full pallet, remove 1 full pallet, divide the entire group of full pallets by 2. Due to the destructive energy and so on. Okay. Write a function called solution which takes a positive integer as a string and returns the minimum number of operations needed to transform the number of pallets to 1. The minimum number of operations needed to transform it to 1. Okay? So the full intake control panel can only display a number up to 309 digits long, so there won't ever be more pallets than you can express in that many digits. Okay, so here we have like solution 4, it's from 4 divide by 2, divide by 2, then we have only 1 left, 2 operations. So we can divide the entire group of full pallets by 2, okay? We can remove 1 full pallet, and which is not shown here in the solution, okay? So there's a third case where you, for example, if you have like 7, so if you would start with 7, then you should not remove 1 but add 1 probably, then you have 8, and now you can divide by 2. 4, 2, 1, okay? So for 7 it should have like so 1, 2, 3, 4 operations. So this one would have 4 operations. Okay, and on the other hand, if you have 9, then you want to remove 1, and then you get to 8, and you can then basically, yeah, quickly go to the to the operation 1. And so basically, we want to. What more information do we have? So we can have input. Okay, so here you get a string passed to the integer, so we need to basically transform the string to an integer before we can do any mathematical operations. Okay, let's check what is else in information we have. So if you watch the constraints file, your code will run inside a Python 2 sandbox. You can use standard libraries. your solution must be under 32 characters. So that's nothing new here. Okay, and again, let's have a look at solution.py. Okay, so it's just the solution, your code here, like we have seen in previous Google FooBar challenges, which I discussed. Okay, so here we have the like the raw code. Okay, what we want to so now we need to write here what we want to accomplish. And so, for example, again, let's copy some test cases. So if you have solution 4, this one, copy, return. So I just return anything now for dummy operation. So if you have print this one, the result should be 2, right? And if you have print 15, then the result should be 5. Because 15 add 1, go to like the next number that is so power of 2. So like we have 2 to the power of x, and this is like, okay, go to the next number and then go down. So like 16, then we have 8, 4, 2, 1. So going to 1, I mean, this is so just an observation here, random observation. It's always very, very fast. So here we basically, of course, we could always go from any element x. We can simply remove one element, go to x minus 1, go to x minus 2, and so on, until we reach 1. So this is like the naive solution. Yeah, it's like the an upper bound for the solution. So you have x operations, actually x minus 1 operation, so 1 operation, 2 operations, and so on, until we have only 1 element left. But this is of course not the most efficient way, because as soon as we enter like a solution that is divisible, that is basically a number 2 to the power of x, as soon as we reach one of those numbers, it's much quicker to divide it by half, right? Instead of going minus 1, minus 1, minus 1. Okay, so the question is then, I think the approach should be to always, so from any number n, we have like a number that is 2x. So any number n is between two numbers. One number being 2 to the power of x, and the other number being 2 to the power of x minus 1. Okay, and the thing is, we always want to go to the number that's closest here. Yeah, so I mean, now we can, like by default, we should go to the one that is smaller, because this will save one operation. But if we are much closer to this number, then we should go to this number, and then we can divide by 2 in one step. And then we can divide by 2, and then it's kind of, this algorithm is already done. Yeah, so we just need to go, like by adding 1 or subtracting 1, we just need to go to the next number that is 2 to the power of x something. Yeah, x minus 3, and so on, until we reach 1. Okay, we also have some information. How many possible so what about the number of digits? Okay, the full intake control panel can only display a number up to 309 digits long. So 309 digits long, so it's a huge number. Yeah, so we can have a number that is like 1, 1, 2, 9, and so on. 1, and this whole thing is like 309 digits long. So it's it can be a huge number. I mean, we shouldn't do too much arithmetic operations there. It must be a positive number, right? Yeah, it will be probably. Okay, so before I start coding, I just want to think a bit about the problem still. Again, so I was thinking, how can we get the next number that is like a number 2 to the power of x for a given number? It's basically, I mean, we know one thing. So if the number is represented, every integer number is represented with a binary sequence, right? So we can have, for example, the number, say, number 0 is represented, say, with a byte value like this. Number 1 is represented with something like this. Number 2 is represented with 0, 0, 1, 0. 4 is represented by 1, 0, 0. Okay, so and you already see what I'm up to. 8 is represented, so the number 8 is represented with 1, 0, 0, 0. Okay, so each time the binary representation of a number has only one bit in it, so one bit flipped on, switched on. Each time we have such a binary representation, we know it's the closest. It's a number that is one number, so 2 to the power of x. And then as soon as we have this number, we can simply boom, 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 go back until we we can quickly move down until we reach 1. So like multiplying a number by 2 will just move the bit by one to the left, one position to the left in the bit string, in the bits sequence, and dividing by 2 will just move the number by one position in the bit string like this. Okay. So basically, if you have like, the algorithm will probably be much more efficient in a binary representation. Okay, so say we have a number and any number consisting of, so now this is a binary representation, a binary number, and now we want to find the closest Okay, so how can we find the closest? How can we go quickly in as minimal operations as possible to the? I mean, you cannot divide by 2 here and multiply, so we need to have an even number. Okay, so if you add 1, so basically we want to remove all ones but 1 numbers. Okay, and here we cannot divide by 2, so therefore, so how can we do it? Must be the minimum number of operations. So the problem is that here, so this was our idea previously. If we have so any number n is in between two of those, right? Two of those numbers to the power of x. 2 to the power of x, and so we need to go to the closest of them. But sometimes going to the closest of them means to, for example, double this number. So for example, if we double this number, so multiply by 2, this is what we can, no, we cannot do, divide the entire group. Okay, so we can only divide, so we cannot multiply, so this is not even possible. Okay, so this makes things easier, yeah, so we can only divide by 2. Let's go back to the binary representation. So dividing by 2 means we simply get rid of one number here, or basically we shift the whole thing one step to the right, correct? So for example, if we divide 8 by 2, then we simply shift this one position to the right, and we have like 0, 1, 0, 0, and we fill up, we pad the remaining positions. So the one position from the left we padded with the number 0, with the bit 0. Okay, what happens if you have like say a bit like 15? So 15 is 8 plus 4 is 12 plus 2 is 14 plus, so this could also be like a starting number. So what if you have something like this? Then we cannot shift by one position, because now we have like here a remainder of 1. So we can either add 1 or subtract 1. If you would add 1, then we would, I mean, have a much easier game here, because then we would reach, like by adding 1 we would reach 16, which is this number, which we can then easily divide. Okay, so they can get rid, and we are done. But what we also can do is like we can also like subtract 1. If you subtract 1, we get like 1, 1, 1, 0. And based on, and now we can divide by 2, which means that we have 1, 1, 1, okay? And we fill up with a leading 0, basically. And so like this number would be 14, because it's like no, it's not 14, it's so we remove, so we actually have -1 at the beginning, which is 14, then we divide by 2, which is 7. Okay, so we have here, we have 7. 4, 6, 7, yeah, 4, 6, 2, 6. No, this is still 14. 6 plus 8 is 14. Okay, so here we have the decimal number 14, and now by dividing by 2 would be 7, so we simply dividing by 2 means that we shift the whole sequence by 1, so we get rid of the leading 0, of the trailing 0 in the bit string, and obtain this one. And here this one is like 1 plus 2 is 3 plus 4 is 7. So here we have the number 7. So this works. So this is like a binary division. I just have to like rethink it again. Okay, so now we have reached 7, and now again we have the problem that 7 is not divisible, basically. So therefore we need to decide whether we want to subtract 1 or add 1. Okay, say we again subtract 1. Of course, if we would add 1, this would be the best thing, because then we would reach 8, which we can then multiply it. But I mean, I just want to see how bad the bad solution is. Say we subtract this one, then again we can divide by half in the next operation. So this way we would it would result in more operations. So this would not be the perfect thing, right? Because each time we have to subtract 1, divide by 2, subtract 1, divide by 2, subtract 1, divide by 2. The better thing is to only add 1 once, and then we can divide by 2, divide by 2, divide by 2. So we really need to double down on this idea that we have a number that is between two binary numbers, and we want to get the closest binary number we can get in the minimum number of operations. And we cannot multiply, so if the closest binary number is, say, this one, then we simply need to add 1, so we need to add 1 a lot. And there's no easier way of doing it actually. Is there? Sometimes there may be actually. So I mean, of course, we can have an algorithm, a naive approach that would just like search the whole space. Yeah. So in each time it's a decision, we can do 3 things. We can in each step basically we can do 3 things. The first one is to add 1. The second one is to subtract 1. The third one is to divide by 2. So we can have a whole decision tree basically. I just wonder if it is the most efficient way of doing it. Okay, so like for any number, so like yeah, so let's call it x. We can now decide to use x plus 1, so it would be like a recursive approach. We can have x minus 1, and we can have x divided by 2, but only if it is divisible by 2. Okay, so in some cases this is possible, in all cases these 2 are possible. And then of course here we can have the same decisions, and here we can have the same decisions, and so on. There are many optimizations which we could use then. I mean, this would be a trivial solution, kind of. Just wonder if I should even try it. I mean, wouldn't it be very inefficient to have this for, say, if you have 309 digits? It's a huge number. So there are many decisions actually which we can do. So it would be a huge tree. Probably the tree would be too large, so it would never actually finish computation. So we must be efficient. Sorry. Okay, still thinking. So I think this conceptual part is really important here. We really need to nail down our concept, our idea, how we approach this. Because otherwise it will kill us. I mean, 309 digits. (32, 64) binary numbers. Let's do some research. So I just want to have a table of the binary numbers. Binary numbers table, just to see. Okay, here we have a lot of binary numbers. So one question I always wonder if, so what, I mean, is it always, do we always have to go from here to the closest number, or would it be sometimes better to divide a number by 2 and then go to the closest number here, because now the closest number is probably closer even. The closest target number, so number that is basically that is how do we call them, that is in the series 2 to the power of x. Sometimes this may be more efficient, I guess so. I mean, because there can be really a lot of steps involved to reach the next number here. Sometimes it's better just to reduce the interval between two subsequent numbers of this series. So therefore it's better to divide by 2 and go into this smaller interval. I think in many cases it will be even more advanced. So it will be an advantage actually to divide as soon as possible, just as a heuristic. I don't know if it's the optimal one, because sometimes it may not be. So in the previous example with this, if you start with 15, for example, it is much better to increase it by 1 than to divide by, or if you start with 14, say. Okay, if you start with 14, you can basically, divide by 2 and increase by 1. You can divide by 2 first, it doesn't really matter. If you are, so here's my thought. So say you start with 14. So here we have 16, which is 2 to the power of 4. And here we have 8, which is 2 to the power of 3, 2 to the power of 2, and 2 to the power of 1, and so on. Yeah. So now for 14, so we now have two options. We can do +1, and then divide by 2, divide by 2, divide by 2. So this would be one path we can go, or we can do this one. So we can divide by 2, going to 7, add 1, divide by 2, divide by 2. Okay, so in this case we have 1, 2, 3, 4, 5 steps. In the second case we have 1, 2, 3, 4 steps. So it's even better. So this is exactly the reason. Here we have to do 2 steps to reach the next number, that is one of our target series numbers, and here we have to do only 1 step. So therefore it's better to first divide by 2. What about 6? Again, for 6 we have like 2 steps to reach this number, and then we have 3, 4, so 2 additional steps, or 3 additional steps to reach the number 1. But we can also divide by 2 if you have, no, it shouldn't be 6, it should be 10, sorry. So it should be 10. So now we can also do 10, we can divide it by 2, then we go into this, to this number 5. So it's like 1 step, and then we can do in 1 step, like 2nd step, 3rd step. So this is also the faster one, right? Here we have to do 2 steps, here we have to do only 1 step. So if possible, it should always be the best thing to divide by 2 if we can, as fast as possible. Okay. So I think again, we have these target numbers. Let's stay with this idea. Okay, so we have, but let's keep it a bit more abstract actually. We have the target numbers. So here we have one target number. Like it looks somehow like this. Okay, so the interval always becomes smaller, and we start anywhere in the interval. Here in this case, so if you have an odd number, then we cannot divide by 2. So we want to reach this part here as soon as possible, yeah. And if you have an even number, we can always do this jump and we can go closer towards our goal greedily. But if you have an odd number, then we cannot do it. So we need to either so go one step into this direction or one step into this direction. Right? So if you have, like, you can divide each interval into like two parts. The first part is closer to the next number, and as a tiebreaker, of course, yeah. So this part, all numbers that fall into this range, they are closer to the left part of the interval, and if it falls into this one, then it's closer to the right part in the interval, and then you should go here. Okay. So therefore, you should always go into basically into the direction of the next interval boundary, if possible. So if you cannot do anything else, so basically you can always do something else. You cannot always divide by 2, but you can always like have +1, -1. But we wouldn't get closer to our interval boundary by doing this -1 thing. And then it's like this, okay? So say we have an even value here. Now we can either directly reach the interval boundary, or if we don't reach the interval boundary, then we can also, instead of adding 1 and going towards the interval boundary, it would be better actually to divide by 2. Because if we divide by 2, the difference between our current number and the interval boundary will reduce, right? It's like in the nature of things. So say we have now, let's make it an x. So this is our current number, x. So so now there's this like difference from the interval boundary to our current number. And this, if you divide the number, so if you enter this smaller discrete interval of numbers, then the difference between our current number and the interval boundary is smaller. I think this is this must be the case. You probably can show that it is much smaller if you divide by 2. So then, and if it is smaller, then of course we have less steps to reach the interval boundary. So it's a good thing, right? So does it have to be smaller? Yeah, I guess so. I mean, it must be smaller because there are just less numbers left. Say we have like all the ticks. These are all the numbers between our current number x and the interval boundary. And now here, because we have much less ticks, so dividing it by 2 basically is a projection into the smaller interval, keeping the keeping the proportions intact. Yeah. So if we are like here, if we are 1/3 to our interval boundary and we divide by 2, then we also are like more or less 1/3 to the interval boundary, right? So for example, if we are half here between those two boundaries, we divide by 2, if this is even possible, then of course we are also in this space here. Yeah. So like we this must be the case. It must be the case because we have just half of the ticks here, and now of course we must have a 1-to-1 mapping from those ticks to those ticks. Basically not in 1-to-1, so we must have, so every second tick here on the left for this larger interval must map to one of those ticks in the smaller interval. Every second, because we cannot divide the odd values. So we can only divide the even values. So therefore, only the even values here will be mapped tick by tick to those smaller ticks, okay? And it will be very regular. It must be regular, like this. So let's get rid of all these things. Okay, so again, so I will get rid of some of those. So again, to show you the idea, I think this is a potent idea which we can examine further. Okay, so we have the interval and we have like the current number x. Now we need to check, is x closer to the upper interval boundary or to the lower interval boundary. If it is closer to the upper interval boundary, then we move, if we have an odd value, we move one step to the left to obtain x tick. So this is an optional operation. It's only if you have an odd value. If you have an even value, so say now we have an even value, we divide by 2 to map it into this space of the smaller interval, to move ourselves closer to our interval boundary. Okay, if now we are again if we again have an odd value, now we need to increase it by 1, so we need to move towards this upper interval boundary, and we always move closer to the upper interval boundary as by 1 step, and then again we divide it by half to reduce the difference, the distance to the next interval boundary. This is our goal, to go to the interval boundary as fast as possible. And now at one point we can reach the interval boundary in 1 step, and then again we are boom, 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 we are done. Okay, and similarly, if we start with a number that's closer to the smaller interval boundary, then of course we will move. So say this is an even number now, then we will directly divide it by 2 to reach this point. It's now closer to the interval boundary. So now say this is also an even value, so now we can divide by 2, no problem. Say now this is an odd value, now we move 1 step to the right, closer to our next interval boundary, and now we can again divide by 2. So this way we will have the minimum number of steps to the interval boundary, and we will quickly reach our interval boundary 1. So you see, it always stays constant. So we always are either in the decreasing mode, or we are in the increasing mode. So for any input number, we will actually only have 2 choices. So first of all, we check, are we in the decreasing mode? So are we closer to the lower interval boundary, or are we in the increasing mode? Are we closer to the upper interval boundary? If we are in this mode, then we only do like divide by 2 or -1. These are our only 2 decisions. And if we are in the increasing, then we also do only divide by 2 or +1. And we only do this if we have, so we only do +1 on our current number if we have an odd value, if our current number is odd. And also we do only -1 if it is odd. Otherwise, in all other cases, if it is even, we will do divide by 2. So this looks pretty efficient to me. Because it's a very simple algorithm, and it should be perfect, and also it's quite efficient. Because of these simple choices, just an if then else thing in our code. So this looks good. And okay, now so this is our mode. Now we need to check. So we need to have this check: are we in decreasing or are we in increasing mode? So this algorithm will quickly go. I mean, now we only have the check. So we need to develop a function decreasing ? And it returns true if you are in decreasing mode. It returns false if you are in increasing mode or so. Yeah. So how can we do this? So for a given number x, how can we determine the next interval boundary? So I mean, one like trivial thing would be to just go over all these, like just map them out. So we have like 2, 4, just bam, 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 calculate all the, like multiply those numbers by 2. and then we can simply compare. Yeah, I mean, simply then we compare the absolute difference between those two, and if they are like negative both, because x is still somewhere here, then we will like go to the next one. So we need to check if is x in the interval. We simply go over all these numbers. We check if x is in the interval, and if it is, then we can quickly figure out the difference between the interval boundaries, and then we know, okay, should we be in the decreasing mode or in the increasing mode. Is this a bad algorithm? Maybe not. Maybe it's not the like smartest algorithm on earth, but so if we have number x, then our runtime behavior is already like logarithmic to number x, so to say. Yeah. So because in each step we do like divide by 2 or -1, and then until we reach 1. So we, like in the best case, we divide by 2, divide by 2, divide by 2. So how often do we have to divide by 2? It's logarithmic to the number basically to our input number. So therefore the algorithm runtime complexity is already logarithmic, which is quite fast. I mean, so and here this one is also just logarithmic complexity. Yeah, so we compute the number, the interval boundaries that are decreasing. So I think this can be done. We can do this quite effectively. Okay, so let's maybe start with some code and check if our idea works. So I mean, there's one case which we also need to discuss, which is if we are directly. So if we are at the half the interval boundary, so it's, I mean, in both cases it would be the same. So we can either go here or we can go here. Then of course we should decrease by 1. Yeah, because I mean, it's just, I mean, just if we reach the higher number, we also need to have one additional step to go to reach the lower number to divide by 2. So therefore it's better to directly go there. But if we are here, if this is our number, now we should go upward, because now it would also take us a step to go here. So therefore, I mean, it like this takes one step and one additional step, and then we can like reach the lower boundary. But going from the upper boundary to the lower boundary also costs only one step. So therefore, we don't gain anything to go to the lower boundary here. So therefore, I mean, the tiebreaker is, so if we are directly in the middle, in between the interval, then we should go, so then of course we should go to the lower, but if we are like one step ahead towards the higher boundary, then we should stick to the higher boundary. Okay, so this is our simple algorithm. Let's map it down, the algorithm. Okay, so we have a current number x. Initially the current number is x, so let's call it x. Initially it's n. So n is a string value, so we know is a string, so we need to convert it to an integer number. And now we have an integer number, and this will be simple because there will be no float or anything. There will be no rounding or something. It's just an integer number which we convert. Then we have like while, we check while x is not equal 1. We do something. Then we have a counter here. Like, what's up with this code? Okay, there was just a thing with the white space. Okay, so so we need to have a number like let's call a variable c. This is a counter. Initially we have 0 operations. Okay, so now as long as x is not equal to 1, 1 is our target value. So forget about all the binary stuff I just started with. How a simple algorithm will do. So as long as the number is not equal 1. So what if it is 0? Can it be 0? positive integer. I don't think so. Okay, so so as long as it is, yeah, we can also have, so while x is larger than 1, maybe it's a bit simpler, because I mean, if x is 1, then we simply return the counter. So now we return the counter. This is our goal, which we want to do. Yeah. So as long as x is larger than 1, we basically do like if decreasing. So this we need to figure out one time in advance. So if decreasing, then we do x minus 1, else we do x plus equal 1. If decreasing, and so not only if it is decreasing, but also if it is odd value. Yeah. So I just have some placeholder now. So if we are in decreasing mode, and then we have our number is basically odd. So no, it's, I mean, it can be a bit more efficient even. So we do like if our number is odd. So only if it is odd, we actually do something with the number, like adding 1 or subtracting 1. Otherwise, we will just divide by 2. So here we have add or subtract 1. Else, if it is not odd, then it is even, so we can divide by 2. Divide by 2. And in each case, like we do counter plus equal 1, so we increase the counter by 1. Okay, so this is our general strategy. Okay, we repeat as long as our variable x, our current value, is larger than 1. We repeat, so we check if it is odd. If it is odd, then we add 1 or subtract 1. If it is even, then we divide by 2. In this step, we increase the counter by 1, because in any case we will have done one operation, and sooner or later we will reach the value 1. Okay, and each time we know so if it is at an interval boundary, we want to divide by 2, right? But then, I mean, it will be odd. So if it is like 2 to the power of x, then this value is divisible by 2 per definition. Yeah. So therefore, we will then, in this case, if we are already reside on interval boundary, we will do divide by 2, divide by 2, divide by 2. So we always divide by 2, and finally we will reach 1 automatically. So we don't even need to be aware that we are currently at an interval boundary. It will just work. If we are close to an interval boundary, then we know we are in an increasing, like in this case we would be in an increasing mode. In this case we will be in the decreasing mode. So we will just decrease if we can. Otherwise we will divide by 2, because then we will be even closer to the interval boundary. Okay, so now we need to add or subtract 1. Subtract, like we can increment or decrement mode. So we can check like if increment mode, we will do x plus equal 1, else we are in the decrement mode, so we will have x minus 1. Now we need to figure out increment or decrement mode, and here in this case we will just like do x divided by 2. Okay, so now in each branch we will modify the value x, and we will increase the step size, the number of steps, number of operations we will store in our variable c. And let's make it a bit larger, this whole code file, so that you aren't confused by it. Okay, so we have the number of operations we store in the variable c. Yeah, we don't even need to annotate it, I guess. So now one thing is left to figure out the increment mode. So how do we know the increment mode? Let's have a small function, def inc or decrement mode. We have a value x, which we pass. Return. So this basically, here we want to, again, we want to check. Let's move out here. Yeah, so here you see in this example, we need to check like the interval boundaries. So let's think about this for a moment. Maybe there's a more effective solution. So I mean, we can't just compute this whole series, like all the values, boom, boom, boom. We do this as long as as the variable x doesn't fall into the interval. As soon as it falls into the interval, we can quickly figure it out. So let's just write the code for this. Probably this can be done very efficiently by converting it into a binary number. So because if you have now the binary number, again, so say we have this binary number, then what is the closest interval boundary? So now this one, so this binary number falls into the interval. So what are the interval boundaries? Basically it's 1, 0, 0, 0, boom, 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 0, and we have an upper interval boundary which is like adding one position to the. So maybe it's not. It's hard to see now. So here we have say we have the number 1, 1, 0. Now we need to figure out the interval boundary. So we like the number 1, 1, 0 is in the interval like 1, 0, 0, 0. These are now binary numbers, not decimal numbers, and 1, 0, 0. Okay, so these are our like boundaries, and now we need to figure out the closer boundary. And now it depends. I mean, the closer boundary is just so we can be very smart about it. We can go over all these digits here. If the first digit is 0, I mean this one will always be 1, right? The first digit will always be 1. If this would be 0, then we would even be in a different interval, because now we also have this as an interval boundary. So if the first digit would be 0, then we would fall into this interval, so it wouldn't be even 0. Okay, so the first digit is always 1, but the second digit now determines if you are closer to the increasing interval or to the decreasing interval. Yeah. So basically, in all cases, we will be, if it is so in all but one case, we so this one means that we are closer to the increasing to the larger interval, with one exception. And that is that every other digit is 0. So if like, I mean in this case it doesn't make sense. So in this case, basically this number is closer to this interval boundary because I mean it's just half. So in this case, it's a tiebreaker. It's just half the interval boundary. So multiplying this by 2. No, basically not. So let's, what are these for numbers? This is the number 4, this is the number 8, decimal number now, and this is the number 6. Okay, so the like 2 plus 3 is 5 plus 3 is 8. So 5 would be the exactly half the interval boundary. So if this would be 0, then of course it would be closer, always closer to the right. If it is 1, then it will be always closer to the left. Is it this already? Is this already the solution? I'm not sure. I don't want to add another mistake here. Just for just with the one reason. I mean, just by trying to be too smart. Okay, so if we, I mean, if this is 1, then we must fall into the larger, into this left interval. So 5 would be the interval boundary here, and 5 would be like 1, 0, 1. Yeah. And also if you have 16, so let's make it bigger. So if you have 16 here, now exactly half. What is exactly half? So we add them together is 24. So is it 12? So now we have 12 as exactly half between the intervals. So the number 12 should be mapped to the 8 as well. So this one is 1, 0, 0, 0, 0. This is 16. This one we already have. Yeah, it's 1, 0, 0, 0. And 12 is basically 1, 0, 1. So 0, 0. So this one is 4, yeah. So we have no, basically it's this one. It's this. Okay. So we have 8. Sorry about this. So this is 8. Digit for 8. Digit for 2. 0, 0. So we have 8 plus 2 is 12. So this one, of course, then should map to the lower boundary. It should go to the lower boundary. So therefore, it's not enough to look at the first digit. In this case, it was enough to look at the first digit. But in this case, not. Okay, so now, so we can optimize later if you want. Okay, so we have like we have a current interval. So lower and upper. Call it L and U. Lower is 1, upper is 2. Okay, why not X smaller than upper? We just need to get track of the upper upper boundary, like upper boundary, let's call it just upper, and it's 2 initially. So, and while x is larger than upper, we simply do upper multiplied by 2. So we double the upper boundary, and sooner or later our upper boundary will be larger than x. So in this case we will calculate lower as upper divide by 2. We use integer division. Also we should use integer division here, because we always want to have integers. Yeah, we don't want to, otherwise division will return a float value. We don't want to have float values. This could kill our code basically. Okay, so we have integer division here. So I'll show you. This will throw an error message. I just will want to show you integer division. So if you have a number, say 8, you divide by 2, then you have 4.0. Yeah, but you want to have 8 divided by 2 integer division, then you have 4. Or 6 divided by 2 is 3. So you always want to have integer division. Okay, so now here we have the lower and the upper interval, and now we check if let's call this function is increment mode, and yeah, so if x, so it is in increment mode if upper, can you have abs? No, it's not the absolute value. So it's like yeah, we simply use upper minus x. So this is the difference between the two. It's larger than lower minus s. Now if it is smaller, only if it is smaller than lower minus s. No, actually then s minus x minus lower. What I'm even talking about, there's no variable s. Okay, so so if upper minus x is the difference between the upper interval boundary and our current value x, and this is a difference between the lower boundary and our current value x. So if like if our difference is smaller, if our distance to the upper interval boundary is smaller, then we are in the increment mode. So then we return true. Otherwise, we return false. So basically, we can simply return this one. Yeah, so we return the result of the operation upper minus x smaller than x minus lower. And so why is that? Again, if so say upper is 16, lower is 8, and here we have 12. Yeah, so then we have 16 minus so x is 12, so 16 minus 12 is 4, and here we have 12 minus 8 is also 4. Then we have 4 is smaller than 4. This is false. 4 is not smaller than 4. Then we have a false operation, false value here. So we are in the decrement mode. Because we return false, that means that we are not, if increment mode is false, so therefore we are in the decrement mode. So at the like exactly half between the interval boundaries, we will be in the decrement mode. If of course we have like 13, then we have 16 minus 13 is 3, and here we have 13 minus 8 is 5. Then we have 3 is smaller than 5, which is true. Then we are in the increment mode. So we simply return this one. Okay, and now we need to call the function here. If is increment mode x. We check it once, only at the beginning. Then we know we always need to increment or decrement. Okay, so this code looks good, right? We don't need to have this comment. It's like, for sure, it's divide by 2. We also don't need this comment. It's like trivial. Now we need to know, like, check is it odd or even. I mean, you can simply check x modulo 2 equals 0. Now equals 1. So yeah, we only want, I mean, if it is, so we can simply use this expression. It's more Pythonic. Yeah, so we calculate x modulo 2 here. If this is 1, then we have an odd value. Yeah, so if we divide x by 2 and we have a remainder, so then it would be 1, so the modulo operation would return 1. Then we have an odd value, so then x is an odd value, and then we need to, of course, increment or decrement. Otherwise, if x is divisible by 2, so x modulo 2 is 0, then we will enter this branch. We will simply divide by 2. Okay? So this way, this is a Pythonic way to check if you have an even or odd value. So this is also done. Like in this increment mode, we can simply call inc. It's a bit more concise. We already have like the descriptionary title function name is increment mode. So it's already clear what we are doing. We want to check if are we in the increment mode or in decrement mode. Okay, so that's a function that should work. We increase the counter by 1 in each loop iteration. In each loop operation we do one thing, right? We either divide by 2, integer division, we calculate -1 or +1 on our value x, and then we increase the counter, and in the end we return the counter. This is what we need to return, right? So here we have it takes a positive integer as a string and returns the minimum number of operations needed to transform the number of pellets to 1. The minimum number of operations, we have shown that this returns the minimum number of operations, and here we have like 15 goes to 16 goes to 8 4 to 1. So we convert to an integer. This is also important. So what happens if we input 1? So this is also to check. If we input 1, then like we convert to x is 1 now, c is 0, so we have 0 operations. We have some value, then is increment mode 1. We set upper to 2, x is not larger, so x is not larger than upper, so therefore we won't enter the while loop. We have lower, which is integer division by 2 of the upper value, so therefore we have the interval 1 and 2. Now we calculate 1, like 2 minus 1 is 1. It's not smaller than 1 minus 1 is 0. So we have like 1 is smaller than 0, which is false. So therefore we have is increment mode is false. While x is larger than 1, x is not larger than 1, x is equal to 1. So therefore we won't enter the loop. We will simply return the counter 0. So we have 0 operations to go from 1 to 1. This is also true. Okay, so let's execute the code. Okay, there was a def solution and so def solution and so somehow this copy pasting thing didn't work. Okay, we have results 2 and 5, so those two are basically are true. So what happens if we are, let's say, in print solution so I mean we can check 16. Here we would expect to have 4 operations, yeah, so from 16 to 8 is 1 operation, 8, 4, 2, 1. So we would expect 4 operations. 16. Then what happens if we have print solution 32? This should result in 5. Then we simply check a few other, so we constructed a few other test cases. So if you have 33, then this should be 6, yeah. So we should reduce by 1, and then we simply go to the next. So here we are in decrement mode. Let's check another one. So we have like 31. Then we should be in increment mode. We increment by 1, and then also we basically reduce the problem to this one. And now what else? If we are say, so what is the direct boundary between 16 and 32? So we have 48, 24. So 24 would be the exact boundary between the exact middle position between 16 and 32. So 16 plus 8 is 24, plus 8 is 32. So in this case, we should be in the decrement mode, not in the increment mode, okay? And decrement mode means like from 24, like 24, we are in the decrement mode, we go to 23. No, basically we, sorry, it's an even number, so we divide by 2, so we have 12. Then we divide by 2, we have 6. We divide by 2, we have 3. We are in the decrement mode. This we figured out initially already. So we now have an odd value. We need to decrement by 1. And now we divide by 2 and we reach 1. So we have 1, 2, 3, 4, 5 operations. 24 should result in 5 operations. Okay, so let's check all of those. We have 2 correct, 5 correct, 4 correct, 5 correct, 6 correct, 6 correct, 5 correct. Okay, it's very efficient. And now let's check a very complicated number, so very, very large number. So this is a large number. Still, I mean, it's very quick, right? We didn't had to wait too long. So let's make it even larger, the number, just to check. Still very fast. It's extremely fast, extremely efficient code. Okay, so this seems to work. Let's take this thing and call edit solution.py. Now we copy paste our code. Solution n, and we paste our code here. Okay, so let's save changes. Luckily we can also try. So what was the command for trying it? So we can verify our solution.py. Okay, it failed quite some tests. How is that? So which other cases are there? Okay, so it's very common. It never works in the first try, or very seldomly. Okay, print solution. So what if you have like 0? So, but 0 couldn't be an input, right? So our solution has the wrong, so it's the wrong solution for if you put in 0, but because I thought 0 wouldn't be a valid input, right? So so I mean, let's be very crude. Try this. If you even need this, so like if n equals 0, return just a quick test. Return 1, because then we simply increase by 1. Now let's save it, and again we verify the solution. Okay, we failed the other test as well, so this is not necessary. Good. So we passed quite some tests. So our approach don't seem to be too add 1, increase 1, or divide by 2. The full control mechanism have 3 operations. Add 1 full pallet. This is here the increment mode. Remove 1 full pallet. Decrement mode. Divide the entire group of full pallets by 2. Due to the respective energy released with a quantum antimatter, pallet is cut in half. It is only allowed if there is an even number of pallets. I think the approach is sound. I mean, if we are at this position here and we divide by 2, then basically we divide the interval boundary by 2 as well. So this one becomes half. So therefore we should never go towards this one. So more than 1 step. Of course, if it is 1 step, then we will go there. But if it is more than 1 step towards the interval boundary, then we will. It's basically much better to divide by 2, because now here x will have only half the elements in between itself and the interval boundary. So therefore it's sound to divide by 2. Always. Okay, what happens if you have a number with 399 positions? So let's have, for example, 309 digits. Let's have a number, say 12 times 150, so now we have 300, 159, no, 154, so now we have 308 digits. Now we add one more digit for 1518 operations. How can we fail so many cases? There must be a conceptual problem, but I don't see it here. It looks very sound to me. You know, if we are exactly half and it's an even value, then we will divide by 2. This is increment-decrement mode. Are we correct here? We will multiply the upper boundary by 2. So can we ever, I mean, if we are in the interval that is closer to the upper bound and we divide by 2, then we are still in the interval that is closer to the upper bound. So therefore we will, sooner or later we will increment it by 1, increment our value by 1. So this increment-decrement mode, I think it's sound as well. So while x is larger than upper, now we increase upper by 2. And we increase upper by 2, so we multiply upper with 2 until upper is larger than x. Then this condition will be evaluated to false. We will calculate the lower boundary. We will check the difference between both. So let me check one thing. Print x in each step. It looks beautiful. Okay, so here you see the operations. We have like 44,188. We divide by 2, we divide by 2. Obviously we are in the decrement mode, so we decrement by 1. Now we divide by 2, we decrement, divide by 2, decrement, divide by 2, divide by 2, decrement, divide by 2, decrement, divide by 2. This seems to work, it looks logical. Did I miss anything from the specification? How can we be even faster here? I mean, how can we ever be faster I mean, if we are in this, say we are in this half, closer to the upper bound, now they are telling me that they are one step, so they need one less step by decrementing it at any point. Like by dividing by 2, they need the same amounts of divisions, right? So if you have like 300 positions, then we have at least 300 divisions by, so more or less, we have more or less 300 divisions, yeah, so because we need to go from here to here to here, so we need to, like each time, no matter where we are in this whole interval between the two, the upper and the lower bound at each step, so no matter where we fall, we will simply enter the other interval. We will simply enter one interval at a time. Integer division by 2. To sort and shift the pallets down to a single pallet at a time. You don't need to do any sorting or so, right? It's Python 2.7. Is it maybe because of the integer division in Python 2.7? So in Python 2, if you use normal division on even values, then it's, so the normal division is integer division. I don't know, so maybe this is it. I don't think that this is a problem, but let's check. So what happens if we use normal division here? It probably fails all other tests, but I just have to make sure. Okay, so it fails the same number of tests. So we go back here, save the changes. What if x equals 2? Then this will not be true. Lower will be 2 divided by 2 is 1. So we have 1 and 2. Upper minus x is, so then in either case we will have the, like, if x is modulo, so Python 2.7 modulo. Okay, that's also not a problem. I just want to check something for Python 2. Start coding. Python. So I cannot change the Python version here, right? Packages, no. So I think it's very sound, our conceptual approach. Are they sure that it's like injection? Let me check something. So they also do the same, yeah? If n is even, we divide by 2. Split manipulation to create as many zeros from LSP as possible. If n equals 3 or n modulo 4 equals 1, yes, n plus 1. So they also have, they decide dynamically whether they are in the increment mode or in the decrement mode. So I want to have those test cases and then compare our test cases against theirs. Okay, so what if, so for example, we have, so let's do this for this large number. Let's take this large number here, put it into our solution function, and now I want to have the result. Okay, so now I print everything. Of course I shouldn't do it. shouldn't print this here. And we want to have integer division. So 1495. Okay, so they got a solution that is better than ours. So, but again, conceptually, so here we have, like, let's stay with me for a moment, this interval boundaries, yeah? So it's like, they look like this somehow. And now we have an upper, so like we divide each interval into two halves, like this, yeah? So these are my blobs, so to say. Okay, so this is the value 1, 2, 4, 8, for example, 16, and so on. So we always have these two blobs. This is the upper part and the lower part. Okay, so now always dividing by 2. So each value here in this upper blob will become a value in the upper blob here. Yeah, so we will always stay in this upper blob. So if we can, we always divide by 2 to stay in the upper blob. And each like lower blob will remain in the lower blob, obviously. Yeah, so we will always be in this half by dividing by 2. And so this remains. And so if you have like any x here, then this x will be now here again, it will be here. It will always be in the lower blob. So in the end we want to have so now here we are always in the decrement mode, right? So we so if in doubt we decrement. Could it be that sometimes it would be better to increment? I mean, if we increment at any point here in the interval, then we will move each time. So in each blob, we will move one step to the left. How can this be better? So what if n equals 3 in our example? So if n equals 3, then the best thing would be to go to 2 and to 1 in 2 steps. If n is equal to 3 in our case, then we are like x is larger, so 3 is larger than upper. Then we have upper is now 4. Now x is smaller than upper, so we leave the while loop. So now we calculate lower is so we have the interval between 2 and 4. So we correctly find the interval between 2 and 4. Now we calculate 4 minus 3, which is 1. And here we have 3 minus 2, which is 1 as well. So 1 is smaller than 1 is false. So therefore we are in decrement mode. So this is false. Inc is false. If inc is false, so if it is 3, then x is of course larger than 1. So therefore, x modulo 2 is 1. So therefore we enter this part here. And now we are in decrement mode. So inc is false. So therefore we go here. X minus 1. Then we are, so now x is 2. In the next case we will have an even value, so therefore we divide by 2, increase step size by 1, so then it works also. Modulo 4 equals 1. So they will have, sometimes they will be in decrement mode, sometimes they are in the increment mode. So if n is even, they always divide, if possible. But if it is odd, then they will be, sometimes they will go into this n minus 1. If n equals 3, or sometimes they will be in decrement mode, or n modulo 4. N modulo 4 equals 1. N modulo 4 equals 1, else n plus 1. So they also use the binary number thing in another solution, but I think it's not necessary. Okay. these solutions. So I just want to like have a few more test cases. Solution 6 equals 4 doesn't work. So if we are at 6, so our algorithm for x equals 6 would be like, here we are, so here we have 8, here we have 4. So if we are at 6, so exactly the middle element would be 6 basically, so 6 is the middle. So therefore we should be in decrement mode. So we decrement by 1. Now we divide by half first. Then we are an element 3. Then we decrement by 1, 2, and now we divide by half to reach 1. So we have, if we are at element 6, then we have 1, 2, 3 steps. So why is solution 6 4? I don't think that he is correct with his with his cases. No, these test cases seem to be wrong. So let's have a quick example. I want to check. So there are some bitwise operations. So we will always have like, so for example, we do some division by 2, like 2000 integer division by 2. But we can also have like 2000. We can also shift by 1 position, and this will also return 1000. Okay, so instead of dividing by 2, we can shift by 1 position. This is what we already have seen in the code previously. So we will do this one, performance optimization. So these assert cases are bullshit. They are not correct. Okay, so so instead of dividing by 2 here, we simply shift by 1 position, and here we shift by 1 position. So this makes it a bit more performant, right? And now, so here we shift by 2. And now there's another operation, and that is checking modulo. Okay, and here we can do the this simple operation. So I will also show you in the shell. Here you have so for any number n, so say n is like again 1000, we can do an element-wise AND operation on this, and to check whether it is modulo basically. Yeah, so this is like a Boolean operation. This is true. So for example, here modulo 2 is true, is 0 is equal to true, because now this element-wise AND operation, so basically in the bit representation of the number, we the AND operation works on the binary number. So we have the binary number, and when is the number divisible by 2? so any number. So say we have the number like 1000, yeah. Then we transform the number 1000 into a bit representation, and this is then I don't know. So actually, I don't know. It's the number of some zeros and ones, yeah, like this maybe. So it's not exactly a number, but yeah. So we transform a decimal number into a binary number, and now we check the last position, the bitwise last position, and this will determine whether it is divisible by 2 or not. Okay, so we can use this small efficiency tweak here by instead of here checking if modulo. Why is this an efficiency trick? Yeah, because modulo is it performs a large number of divisions to do this. Okay, so here if this is 0, then it is divisible by 2, and if it is 1, it is not divisible by 2, and in this case we want to perform this operation. So for example, in this case, if our number x is, say, x is 1001, and now we have this operation x and binary element-wise AND operation with 1, with the 1 value. This is equal to 0 is false, it is 1, so therefore it would return false, so therefore we are like it's not divisible by 2. If it is not divisible by 2, yeah, then then we should enter this branch. We should increment or decrement. Okay, so this makes it a bit more efficient even, so let's check. Okay, now we have other solutions a bit. Probably I did one mistake here. For up, okay, here we shift by 2. We should only shift by 1, obviously. Right. Okay, we shift only by 1 position, yeah, otherwise you would divide by 4. Actually, we don't want to divide by 4. Okay, now we have like 2, 5, 4, 5, 6, 6. 2, 5, 4, 5, 6, 6. Okay, but actually we don't get any other results, so I will still try. If this works, maybe it was a performance thing, I don't think so, but no, save changes. Didn't pass any additional tests, so we don't actually, just an improvement in the code. So they also have the simple algorithm. If the number is even, divided by 2, otherwise increment or decremented by 1. And here they say prove to yourself that if it is 1, you'd rather decrement a number. But I mean, if it is 1, we don't want to decrement or anything, because we have like, we are already there. I don't understand exactly what he's thinking. And if it is 3, if the number is 3, you'd rather increment it to 4. So they say if we have 3, we want to go to 4, go to 2, go to 1, which is like 3 steps, right? I don't see it. So why should it be better? Why should... I've already seen in this case here. He also argues that if use bit manipulation to create as many zeros. So they also check modulo 4. They check if n equals 3, then they want to decrement it. If n modulo 4 equals 1. Decrement it. They say we should look at the remainders modulo 4. If the remainders modulo 4, if it is 1, you'd rather decrement a number. If it is 3, you'd rather increment it. Modulo 4. So they say we have the remainder classes. Okay, so this is also interesting because now they say, so we are in each step, we are like in a remainder class. So it's again like a state machine. Like this, right? So if we have, if we are in this one, in this remainder class, so something modulo 4, then it's divisible by 2, so we simply divide by 2. So this is the fastest approach, right? This is always the case if you have an, so in this case we simply divide by 2, and we stay in the same, no, maybe we don't stay in the same, but here in this case we want to like divide by 2. Like basically if we are in this state, we want to divide by 2. If we are now, if we divide by 2, then of course we can be in any other case here. Yeah, so like we can either fall into this, in that, in this, or in that case. So in this case we also should divide by 2. So if it is modulo, if you are in the remainder class 2. Because if you divide by 4 and then we are in the remainder class 2, then of course we can also divide by 2, it's not a problem. But if you are in the remainder class 1, and we increment our value, increment, so now we can do this +1 here, or we can do -1 and reach this remainder class. In this case, we can do +1 to reach this remainder class, or we can calculate -1 to reach this remainder class. In the end, we want to have 1. So we want to be like 1 modulo 2 is 1. So we want to be in the remainder class 1, right? Okay, so what in the end? So what if we have x equals 2? Don't yet see it exactly. Do -1. Do -1 if we are modulo 4 is 1. We do -1. Okay, so bit manipulation. Doesn't seem to be correct, my assumption that if we are in the increment, so that we are always be either in the increment or in the decrement mode, and this never changes. So I think we should check it on a case by case. So let's again have a look at the binary numbers. So say we have like the binary, this one, then decrementing, so then dividing by 2 would simply shift it, yeah, by 1 position. Like we check this here, if it is modulo 2, then we can simply divide by 2. So if this is 0, so to say, then we can do divide by 2. Otherwise, this will be 1. Okay, so then we'll have, say, a string like this. So it will be 1. So we cannot divide by 0. Now we can either decrement or increment it. If we increment it, then we will have a 1 here. And if we decrement it, this will be a 0. So we want to generate, okay, now I see. So in each step here, we want to, yeah, okay, so now this makes more sense. So actually, we want to create as many zeros as possible, right? Because in the end, if we have zeros, many zeros, so if you have only zeros with one exception, with one bit value 1, then we can we are almost done, because now we have to divide by 2, divide by 2, divide by 2, divide by 2, right? So in each step of the algorithm, we want to either add 1 0 or we remove 1 0. So actually, or we remove 1 digit. So we in each step we add 1 0, so we create a new 0, or we remove 1 digit. If we can remove a digit here, if it is 0, then we will of course remove it. So we will divide by 2 and remove the digit. If we cannot, so if this is like 1, then we cannot simply remove it, so we need to add 1. So now, but here in this case, if our like modulo 4, so from now we can check this bit. So now we have two options. We can either move to this number 1 1 1 1 1 0 0, or we can move to this number 1 1 1 1. So we have like 5 ones, right, the beginning, and then we have 1 here and a 0 here. So these are the two possibilities we have. Yeah, we can either move into this state or in that state. In this case, we can of course remove 0 in the next two steps. So this is like a good thing. But in this case, we can only remove it once, and then again we have this element 1, this digit 1. So we need to like get rid of this again. So this like takes us another additional step. So in two steps we have only like transformed this into a 0 and removed 1 0, and here in two steps we have removed 2 zeros. And then after that we are in the same position, right? Yeah. So after doing these two operations, we are in the same. Here we need to transform this into a 0, and then we can remove it. So this takes us 3 steps, and this takes us 2 steps to be in the same place. Yeah. So no matter what is the prefix here, we are at the same place now, but this just took us 3 operations. So therefore we need to check this second last bit. If it is 0, then by adding 1, we will transform it into a 1. So therefore we don't want to add 1. So this here is +1, and this is -1. Okay, so in this case, if our second last bit, and we can check the second last bit by calculating modulo 4. Yeah, so because so this is yeah, so we will have a look at this in a moment. Okay, we check this second last bit. So if this is 0 and we add 1, then it will be 1. So then we will have introduced another 1, which is not what we want. So in this case, so this one will be a 1 in any case, right? So therefore we only, so we can either add 1 or we can remove 1. So in this case, if you have a 0 here, then we want to calculate -1. If you have a 1 here, we want to calculate, if you have a 1 here, so say now this would be like a 1 value already. Then of course we want to add 1 value, because now if we add 1, we get we produce a new like 1 0 and 1 0, and add another, like here we would produce another 0 0 0 0 0, and then we will have basically a lot of zeros. So therefore we can then quickly go back to our algorithm. Okay, so therefore we calculate modulo 4. And now if you calculate modulo 4, we get either the remainder 2. If you have the remainder 2, this means that we have a 1 here. Yeah, so then remainder 2 means it's no, remainder 3. So let's think about this. So how can we check whether this bit is a 1 or a 0? So here, to check whether it is a 0, we just perform modulo 2. To check if it is a 0 here, we just perform modulo 4, right? And to check whether 0 is here, we just perform modulo 8 and so on. So I think this should work. Okay, so let's try this code. So this increment mode is actually not the way to go. Here this is correct, this part is correct if x, so this checks if it is modulo 2, so to say. And now we can check if x modulo 4 equals 1. So here again, if x modulo 4 equals 1, in this case we want to add one value. No, so if it is 0, so then maybe let's start with a 0. So if it is 0, if this one is 0, so we have remainder class 0 here, modulo 4. Then of course it would be divisible by 2, so we can have either, so we can have two cases, like the case could be 1 here. Let's write this odd. X is odd. So in this case we know x is odd. And now we can have either x modulo 4 is either 1 or it is 3. So it must be 1 or 3, right? And if it is 1, so then these two digits will be 0, 1. So therefore we will have a 0 here. In this case, we want to calculate -1, right, to get to this branch. This is what we had initially. So if it is 1, then we want to calculate -1. If it is 3, this means that we have a bit, so that we have these two trailing bits here. They are both set, and now we want to add 1, because if we add 1, then we generate as many zeros as possible. Now we generate not only 1 but 2 new zeros. Yeah. So if we would do -1, -1 would lead to 1 0 as trailing bits, but add 1 leads to 1 0 0. Okay, so it leads to one more 0 value, and therefore we like have generated one more 0, and we would have to perform one less operation in the future. So therefore we will have gained a lot, basically. Yeah. So even sometimes we will even have, so if there was 1 0 more, then we would have even produced one more 0. So we produce at least 1 0 more, maybe more. Maybe we produce more than 1 0 more. So therefore it's much better in this case if we have 1 1 in the bit representation, which is 3. So if we have modulo 3, then we want to increase by 1. So in this case we calculate +1. Okay, and if possible x is even, then of course we divide by 2. Okay, so let's check our test cases. We have 2, 5, 4, 5, 6, 6. So again, we have the same solutions, but here we have a smaller solution for our previous, for our like extreme case here. So let's check whether this even shorter, even more concise version is basically accepted. Save changes, and let's verify. Now still we have two failures, and I think I already know why we have them. So there are some So I think there's an exception. So if, like in I said that if we have 1 1, then we want to do like +1, right? And if we have 1 1 so if there's any bit string with some values in advance like this, and maybe even more, then we want to add 1, because this in the case will generate most zeros. But there's one exception. If we have only 1 1 as a bit representation, this is like the decimal value 3. If you have the decimal value 3, then in this case we don't want to calculate +1. Now we want to calculate -1, right? So if we are in case 3, so if x is, if like the whole value for x is the integer 3, then the binary representation would be 1 1. In this case we don't want to calculate +1. In this case we want to do -1 to reach 2, and then we will have directly this yeah, it's like a border case, and you need to be aware about this border case. So if x is odd, in this case if x is 3, then of course we want to like change it, we want to add or -1. But if it is modulo 4 equals 1, this would be true for 3. So 3 modulo 4 is 3, so we would land in this case, but we don't want to land in this case. In this case we want to check or x is 3. Yeah, so if x is 3, then of course we want to reduce it by 1 to reach the case 2, and then we want to divide by 2 to reach 1. So, and get rid of all the solutions here. Okay, and verify it. Now it should work. Now I'm optimistic. All test cases passed. Okay, so now we found everything. Submit solution.py. Yes, we want to submit. Yeah, and we reached the next part of level 3. So now I will go into this challenge later. Okay. Copy. Good, then see you in the next video. Bye.